Dear students, in the last class we discussed some properties of a cyclic group, order of a group and some theorems we have to prove in this. Today's lectures we have also start some properties of a cyclic group and we have to start with the theorem. We end with the last lecture. So, that the theorem is let G be a group and G is the any element of a G with the finite order. Then if G to the power k is equal to identity, if and only if n divides k, if G to the power k, G to the power r, if and only if k congruent to mod k congruent to r mod n, and the generators is G generated by this all n minus e g square and G to the power n minus 1, and the elements of a G square and G n minus 1 are distinct. So, I just again recall today lecture with this theorem, and then we have to try to some examples, one or two examples on this theorem. So, I just quickly recall this proof again, because we have to prove that G to the power k is equal to identity if and only if n divides k. So, we use prove this result by using the laws of exponents. If G to the power k is equal to identity, then by the division algorithm there exists some q and s belongs to the z. This k can be written in the form of q n plus rs, because G to the power k you have a is equal to identity. So, this means we can write G to the power q n plus s, and this can be written as a G to the power k is equal to identity. Then we have to just write G to the power q n to the power q into G to the power s. So, we just said that G to the power s can be written in the form of G to the power k into G to the power k minus qn, and G to the power qn is equal to identity, and G to the power k is also identity. That means ultimately we have to show that G to the power s is equal to identity. But you see s is equal to, you have s is strictly less than n. So, if since s is strictly less than n, so this contradicts the minimality of a n. So, this is only possibility when s is equal to 0. So, if s is equal to 0, then we have a if s is equal to 0, then clearly we have to just say that k is equal to, you have a qn, and k is equal to qn means we have a right that the n should divides k, we have to just getting. So, this means k is equal to qn. So, this means simply we say that this is clearly is a n divides the q. So, first part is proof. The conversely is very trivial. We have to n divides the k, that means if n divides the k, then k can be written as a some element of a z into k. So, we just take n r, where r is the element of a z, and so we have to G to the power k is equal to G to the power n r, and G to the power n to the power r. G to the power n is equal to identity, the group is a finite of order n. So, G to the power r is always as identity. So, this means we have to ultimately show that G to the power k is equal to identity element. Now, the second part is saying that if G to the power r is equal to G to the power k, if and only if G to the power k minus r is equal to identity, and we have given this condition, and then we have to show that k is congruent to r mod of n. So, this means we can say that, this means clearly say that n should divide k minus r. So, this implies that n should divide k minus r. So, if G to the power k, G to the power r, and this is all element of a G, then we have to just write as a G to the power k, G to the power minus r is equal to G to the power r, G to the power minus r, and this is equal to, you have a giving the identity. So, this means G to the power k minus r is equal to identity, and then the part 1 is saying that if g to the power k minus r is equal to identity, then he say that n should divides r n should divides k, but k is k minus r. If n divides k minus r, then we can say that k is equal congruent to r, and you have a mod of n. So clearly, if we have a g to the power k is equal to g to the power r, if and only if g to the power n should divides n should divides k minus r, and then we have to show that k a congruent to r mod n. The reverse part is very clear. If we have a clearly, we just say that if n should divides this is we have a clearly, we can say that is conversely part is k congruent to r mod n, then we have to n should divides k minus r. If n should divides k minus r, then the part 1 is say that g to the power k minus r is equal to identity. Then we have to g to the power k, g to the power minus r is equal to identity, and then g to the power k, g to the power r minus r, g to the power r is equal to e g to the power r, because all the elements of this. So g to the power k into identity is equal to g to the power r, and then g to the power k is equal to g to the power r. So conversely, we have to just say that we get that trivially we have to show that this two conditions, if g to the power k is equal to g to the power r, then g to the power k is congruent to mod r congruent to r mod n, and similarly we have to prove the other part. Final part is saying that if we have a E1, E2, En are the generator by G, so we have to, and is a all are these elements are distinct. So this is one way is very clearly we have just as trivially we can say that this set is already contained by generated by contained in the generator of a G. Now we have to do reverse part to prove the other inclusion. Let x is the element of a this. If x is the element of a this x is written some powers of a g. Suppose x can be written as a g to the power k. For some k is into this belong to the z. So x is written in this form. This means as a part 1 by using the division algorithm, then k can be written in the qn plus r, where r lies between 0 to n minus 1 less than equal to n minus 1, and g to the power k. So x is equal to g to the power k, then we can say that x is equal to g to the power k, and g to the power k can be written as qn plus r, and then g to the power n to the power q and r, this is equal to identity element. So e equal to g to the power r, then x is equal to g to the power r, and g to the power r nothing but is equal to r is belongs to the z, and r lies between 0 to n minus 1. So g to the power r belongs to the this e g and this thing. So we can just say that x is the element of a clearly x is the element of a, initially we have to taking this element of a this G, and then we have to show that x is the element of a this set. So clearly this generator can be written this conclusion into this form. First way we have to show that this is trivially containing this one is trivially containing into this. So by these two property we can say that generator of a G is equal to E G E square and then whole indices. Now next first we have to show that these all the elements of a E, G, G square up to Gn minus 1 all are the distinct elements. So suppose we have to assuming that suppose Gk or Gm are the same, where k lies between 0 to k m, and m is also less than equal to n minus 1. And if it is equal, then clearly we can set g to the power k minus 1 is equal to identity element. So we can say that m minus k is lies between 0 to n, and if it lies between 0 to n, and if we can say that this g to the power k minus 1 is equal to identity, so we can write n should divides m minus n minus k is equal to 0. If m minus k is equal to 0 implies that n is the smallest positive power of g, which is equal to E, hence all the elements of this are distinct. So if we have say m minus k is equal to zeros, m is equal to k, then this is powers are the series, n is the smallest positive integer of G which is equal to identity, hence all other elements of this are distinct. So, this complete the proof of this theorem. Now, we have to using this assertion of this theorem, it says that order of a G is equal to n and G to the power k is equal to identity if and only if n divides k. Now, how to the following example illustrate how useful this. So, we see U19 and then you know that the element of a U19 is equal to 1 to up to 18. So, all the element 1 to 18 are relatively prime to 19, they are the member of this. I choose a for example 4 and 4 to the power 3 because order of this is equal to clearly U19 is equal to 18. So, that is the total is 18 elements are there. So, order of this U19 is equal to, or you can say that phi of 19, phi 19 is equal to, you have a clearly prime. So, and phi p is equal to, you know that phi of Euler function phi of p is equal to p minus 1. So, phi of 19 is equal to, we have a 19 minus 1 is equal to 18. So, order of this is equal to 18. So, we just take a one of the elements, suppose 4 is equal to 4 to the power 3 is equal to, we have a 7 and 4 to the power 6 is equal to, we have a 11, and then we have to further go into this 4 to the power 9 and then 4 to the power 9 is equal to 1. So, order of 4 divides the 9. So, this is order of n divides 9 by the theorem previous theorem is saying that n divides the order of a k. So, if g to the power k is equal to y, so 4 to the power 9 is equal to identity and then you have a n is equal to, you have a 18, then clearly 18 divides the 9. So, we have a by 9. So, this means by the theorem clearly this if this order of g to the power k is equal to identity, then n should divide the order of. So, g to order g is equal to, we have taking a 4 to the power 9 is equal to identity element. So, we can say that by this we can say simply is 18 n is 18. So, 18 should divide 9. So, now the order of a 4 is possibility is the divisor of a 9 is a 1, 3 and 9, and then clearly for 3 we have a excluding here and 1 is also excluding, the only possibility is order of this 4 is a 9. So, only possible of order is equal to, we already eliminate 3 here and 4 to the power 1 is equal to already 4, so eliminating 1 also. So, only possibility where this is giving identity is 4 to the power 9. So, for order of a 4 is clearly is a 9. So, the only positive. Now, for other things he is saying that if we have a g to the power r is equal to g to the power s, if and only if, then n should divide by r minus s. So, we use this property for. So, this means order of a 4 is equal to, we have a 9 and 4 to the power r, 4 to the power s is the same power when 9 should divide r minus s. So, we take this 4 to the power 2 and 4 to the power r 11 is equal to 11, these are the same because we have to taking r is equal to, we have 2 and we have take s is equal to, we have an 11 and then by the property say that n should divide r minus s, and here you have a k, sorry k is you have a clearly you have a 9, order of this is equal to 9. So, 9 should divide 11 minus 2, clearly 9 should divide into this, but in this case you see the second case 4 to the power 6 is not equal to 4 to the power 14. Why is not equal to? This means 9 does not divide 14 minus 6 or 6 minus 14, vice versa. So, 9 does not divide the 14 minus 6. So, that means we can say that 4 to the power 6 and 4 to the power 14 are not the same, but 4 to the power 2 and 4 to the power 11 are the same. So, this means when 4 to the power 2 are the same, only when 9 it should divide the 4 to the power r minus s. Whenever 4 to the power r minus 9 divide the 4 to the power r minus s, then we can say that 4 to the power r is the same of the 4 to the power s by the previous theorem. Okay, now we have to transform that the same theorem for in the case of a we have a not a finite order of a G is not a finite, let G be a group and G is the element of a G, but order of a G is infinite, then we can say that G to the power k is equal to identity if and only if k is equal to 0. If in the case of a finite, we can say that n divides the order, n divides the k, and then we G to the power k is equal to G to, is the same if and only if k is equal to, if both the k is equal to k and r the same, but in the finite case we have to show showing that k congruent to r mod n, and again we have to just say that and all these powers of a G are distinct. So we have a going to E, G, G square, G inverse, and we have all these things. So this means in this case, but all these powers of a G are distinct. So we just sketch the proof of this. Let G is equal to 0, then we have identity element, and if G to the power k is equal to identity, we are assuming that k should be not equal to 0. So if G to the power minus k can be written as a G to the power k to the power inverse, and then G to the power k we have to identity, and we have a e to the inverse. E inverse is also is a e, so we can say that E inverse is also t. So hence G to the power n is equal to identity for some n is greater than 0 strictly, which implies that order of a G is finite, and that contradict the hypothesis, because we have two hypotheses is this order of a G is infinite, but we have to show that G to the power n is equal to identity means for some n greater than 0, which implies that the order of a G is finite, and that contradict the our hypothesis. So what is the possibility is G to the power k is equal to 0, all G to the power k is equal to identity only when k is equal to 0. The first part is this theorem is a proof is completed. Now another part is saying that when we have a G to the power k and is equal to G to the power r, and by the this we can say that because G to the power k r are the element of a group. So G to the power inverse is also the G to the power k minus r is equal to identity. Hence by this G to the power k minus r is equal to identity, by the first result we can say that k minus r is equal to 0. So that is k is equal to r. That is a trivial proof into this form. So by using the first part we can getting into this. The last part is because we have to show that all G are distinct. So generator of G is G to the power k, k is in Z. So by the definition of this generated G, these powers are distinct by the second condition. Whenever we have to taking G to the power k or G to the power r, and then by the first condition is say that k minus r is equal to 0, so k is equal to r. So this means all the powers of this set third one, all the powers of this sets are distinct. So we have to complete the proof of this theorem. In the case of a finite, we have a proving different way, and then if we have a infinite set also we have to show that. This means G to the power k is identity, then k is only possibility is 0, and G to the power k G to the power r then only possible when k is equal to r, and all the powers of a G when n k are the element of any integers is also all are different there. So now we have this corollary from this. If G is an element of a group G, then order of a G is the same as the order of a generator of a G. So we can say that order of a G, and we have previously proved that order of a G and order of a G inverse are the same, but now we have to say that order of a G and order of a generator of a this cyclic group G is also the same. Proof is this: simply suppose we are assuming that order of a G is equal to n. Order of a G is equal to n means G to the power n is equal to, we have some identity element, then G to the power n is a member of this generator, then order of a G to the power n is equal to identity 2. Then the third part of this previously theorem, because we can say that all they are finite element, if the group is a finite, then all the powers are the distinct. So, this means order of G is clearly we have a generator of this is equal to n. So, this is trivially this. Now, we have to just say that if G is a cyclic group of order n, then it is straightforward to determine the order of all the elements of a G, and this summarize the following theorem is saying that let G is equal to the generator of a G be a cyclic group of order n, and k lies between G to the power n minus k, and we can say that if G is equal to GCD of a Kn, we can say that M is equal to some GCD of the Kn. If order of G to the power K is same is N should divide the M, or we can say this can be written as N should divide the CD of K and N. If we have a this group of K lies between two into this form. So, we can simply this n divides m in place of m, we can just say that m is equal to simply m is equal to we can say that GCD of K and n, this one. So, I just say that proof is very simple. We take let k is equal to some ms and n is equal to some mt, then g to the power k m divides n divides m can be written as a g to the power k n over m, and k is equal to ms g to the power ms n over m, and then you have a just say that g to the power n to the power s, and g to the power s is n is equal to identity. So, if this is identity, we can say that e to the power s is also identity, and then clearly says that g to the power k to the power n by m is equal to identity. Then we can say that nm divides the order of g to the power k by the our theorem. If g to the power k is equal to identity, we can say that k divides the order of a g to the power k. So, by this we can say that this clearly, and now suppose that g to the power k is equal to r is equal to identity, then g to the power k r is equal to identity, and j to the power k r is equal to identity, that means n should divide the k r. So, if by the theorem property we can say that clearly n should divide the k r. So, hence n by n divides the k r k by m into r, since nm divides, since m divides n divides m, k divides m are the relatively prime. So, these are two relatively prime, it follows that n divides m divides r, and hence nm the smallest power of g to the power k, which is equal to e. So, order of a g to the power k is the same as n divides m. So, a cyclic group, now we have to just complete the proof of this. Now, a cyclic group G generated by G can have other generator. So, our next theorem explicitly describes all generators of a finite cyclic group. So, he is saying that if G is a generated be a cyclic group generated by G and order of a G is equal to you have a n, then G is a generated by G to the power k if and only if, and then k and r relatively prime. So, if order of a G is equal to n and k of n are relatively prime, then we can say that G can generated by some generated by G to the power k also. So, if G is the generator of a G and then order of n is equal to n, k and n are relatively prime, then we can say that G can also generated by G to the power k. If G can generated by G to the power k, then only possibility is k is relatively prime to the order of a G. So, let G proof is let G is equal to generated by G to the power k. If G is generated by, then G is the element of this generator, and if G is the element of this generator, then G can be written as a some Gk power sum of a G to the power k, and some R is the element of a Z, and then we just say that so G to the power 1 is equal to G to the power R, but we can say that n should divides 1 minus. So, if we have a result is G to the power R is equal to G to the power S, then we have the finite order of a G is a finite, then n should divide r minus s. So, here also n should divides 1 minus kr, and if n divides 1 minus kr, n can be so 1 can be written as a qn plus kr, and if 1 plus 1 can be written as a qn plus r, then we have know that this q n and k are the where q is the element of this, then n and k are the relatively prime. That is the result in the by the division algorithm we can easily prove by this result using properties. If G is the generator by generate G to the power k, then we have to show that k and n are relatively prime. Now, we have to go the reversely. Suppose k and r are the relatively prime. If k are relatively prime, then this condition must be hold. So, GCD of Kn is equal to 1, then if GCD of Kn is equal to 1, so we can say that 1 can be written in the form of a this AK plus Bn, then A and B are the some integers, and we have to take a G to the power 1, G can be written as a G to the power 1, and G to the power 1 is G to the power, so here we can write G to the power 1 is equal to G to the power AK plus Bn, and this G to the power AK can be written as a G to the power K to the power A, and G to the power N to the power B, and G to the power K this to the power A. So, G to the power K to the power A, and G to the power N is equal to identity, because we have a order of a G is equal to N, and this is E to the power B, and this is equal to again this is the same as G to the K power A. So, G can be written in the form of a GK to the power A. So, G can be means is a some power of a G to the power K. So, is generated is belongs to the generator of G to the power K. So, which implies that this is the element of a G, then G can be written as a generator of G to the power K. So, if we have a GCD is equal to GCD K of n is equal to 1, then we can by the property of this, if GCD is equal to then 1 can be written in the form of a sum of a these two AK plus Bn, A and B are the elements of some integers, and then we use this property, and we can easily show that this satisfy this condition. Now, we have to take this example by this. If G is this cyclic group generated by 10, then the generator of a G are the powers of a K only when we have just as a generator of a G to the power K, when K and 10 are relatively prime. Now, clearly K and K is equal to 1 and 1 and 10 are relatively prime. So, G is the so if we have a K is equal to 1, then we have a clearly 1 and 10 are relatively prime. So, we have a G is the generator G to the power K. So, we have to just say that, and now we have to take a 2 and 10, and then it is not equal to 1, clearly is not a generator. So, we have a 3 and 10 is equal to 1. So, that means G to the power clearly G to the power is this, then G to the power 3 is a generator, and then we have to take a 4 and 10 is not relatively prime. So, 4 is not a generator, 5 and 10 is also not a relatively prime clearly, and then we have to say that 6 and 10 is also not a relatively prime. So, we can say that now 7 and 10 they are relatively prime. So, the G to the power 7 is also the, now we have to 8 and 10 are not a relatively prime, but 9 and 10 are the relatively prime. So, this is equal to G to the power 9. So, we have to just say that you can say that 1, 3, 7 and 9 are relatively prime to 10. So, this means G to the power 3, G to the power 7 and G to the power 9 are the G to the power 3 and G to the power 7 and G to the power 9 are the generators of this. In particular case of additive cyclic group of Z10, now you know that Z10, and we have to we can say simply is equal to, we have a 1, 3, 7 and 9, under the generators are the residue of 1, 3, 7 and 9, because we have to just say that under they are relatively prime. So, we can say that they are all the generators of this group. Suppose we have to take a one more example. We take a, let G be generated by G, and order of a G is equal to 12. So, we have a n is equal to 10. What is a k is equal to 5? So, we have a GCD of a 5 and 12 is equal to 1, then 5 and 12 are relatively prime. Since this the element of a G to the power 5, we generate the entire group. So, G is equal to generated by G to the power 5. We can find easily by this is a generator in case k is equal to 5. Now, we have another, if case k is equal to 4. If k is equal to 4, then GCD of 4 and 12 is equal to 4. So, GCD of k and 4 are relatively prime. So, we have the G to the power 4 will not generate the entire group. Instead of G to the power 4 will generate the proper subgroup of a G of order 3. Okay, because we have to just say that, and we just say that we have order of G to the power k is equal to, we write in the form of this n divides GCD of k into n, and that is equal to 4, and then we can say that this is equal to 3. So, in place of k we can write here is a 4, so we can write as a 4 and this is equal to same. So, not a problem here, we just leave as it is. Okay. Okay, in case of a 7 or 12 are relatively prime. So, 7 of 10 is G to the power 7 generates the whole entire group of G. I have to stop this lecture here, and then we have to continue next class some more examples in this. So, thank you very much.